Welcome to Mavinhub Physics Lab. Today we'll be talking about NECO 2021 Physics Practical. Specifically, we'll be talking about the question number 3. Question number 3 is under electricity in physics. So first and foremost, let's talk about what you'll be given, the apparatus that you'll be given on the day of practical. So you'll be given a resistor of 2 ohms, and that resistor will be covered. In other words, they will try to conceal the ohm, and it will be labeled X. You'll be given a resistance box. We'll talk more about what a resistance box is used for and what it does basically. You'll be given a key or a switch. You'll be given 1 or 2 ammeter, depending on the nature of the question. You'll be given an accumulator of 2 volts or 2 dry cells each of e.m.f of 1.5 volts. In most cases, you'll be provided with e.m.f battery. That's a battery whose e.m.f is 1.5, 2 batteries, basically. Then you'll be provided with connecting wires. So the question now is, what is the likely question that will be given to you based on this apparatus provided? So that's what we'll be discussing today. We will go through an experiment that will make use of some or all of these apparatus, and I will also guide you on what the objective of this experiment is all about. And we will perform the experiment, take readings, plot graph, and get our results. So, mind you, we'll be using Mavinhub Physics Lab to do this simulation. Mavinhub Physics Lab allows us to perform a lot of experiments, including experiments involving electricity. So let's get into it. So this is Mavinhub Physics Lab. So we're going to go right into the experiment menu and go straight into the experiment that we'll be talking about today. So the experiment is under electricity. So we're going to go to the electricity menu. Then under electricity, we are going to take a look at experiment 3. So experiment 3 is the closest experiments in Mavinhub Physics Lab that has virtually all the apparatus that you'll be provided with in NECO 2021 Physics Practical. So let's take a look at the experimental setup. Mind you, this may not be exactly what you might be. This may not be the exact experimental setup, but this is very similar to whatever experimental setup you will see. And the objective in this experiment is, I'm very confident that the objective of this experiment is going to be the same as the objective of the experiment that NECO will set in 2021 Physics Practical under electricity. So if you can master this, then you'll be very, very prepared for the actual exam, because they share the same apparatus and they share the same objective. Okay, so let's get into it. So the circuit diagram is given us as seen here. So here in this particular experiment, you are expected to have 2 ammeter. So you also expect to have a resistance box and the standard resistor, which is 2 ohms. And the resistor that will be given to you will be covered, in other words, be concealed and marked as X. Okay, so what's the whole objective of this experiment? The objective of this experiment is to calculate the resistance of the resistor given to you, of this resistor given to you. So at the end of the experiment, they are trying to guide you on how to actually compute R0 which is the resistor that is labeled X. So that is basically what the objective of this experiment is all about. Okay, now you are also going to be provided with a key and also batteries. And the batteries will have a total e.m.f of 3 volts. So these are the things that will be provided to you. Now let's take a look at the actual diagram of the apparatus. So here we have the battery of whatever volt that will be given to you. Then here we have the standard resistor. Here we have the key. We have the first ammeter, we have the second ammeter, then we have the resistance source. So this diagram shows you how to actually connect the whole apparatus using the connecting wire. You need to notice something. You need to understand that when connecting ammeter, the positive terminal of the ammeter must be connected to the positive terminal of the battery, and the negative terminal of the ammeter must be connected to the negative terminal of the battery. If you trace this wire, it eventually goes through this part and eventually goes into the negative terminal. And the same thing goes to this. This goes towards the negative terminal. So it's very important to understand how to properly connect ammeter. This diagram will tell you how to do that. Okay, so the next thing is, what is a resistance box and how do you read a resistance box? Also, what is an ammeter and how do you read an ammeter? We will talk about that later on. Let's continue. So once again, here we have the apparatus. The difference between the apparatus here and that of NECO is these ammeters. NECO only stated one ammeter. It may be one or two, I'm not certain, but in this particular experiment, we expect to have two. So that's where we have the kind of difference. But at the end of the day, the objectives are the same, and the results will be, the setup will be similar to a very good extent. Okay, let's talk about the procedure. Here we have the procedures. The first thing you need to do is to measure and record the e.m.f of the battery. So since we know that our e.m.f is 1.5 volts each, so altogether we have 3 volts e.m.f. e.m.f stands for electromotive force. So number 2 is to set up a circuit as shown in the diagram above with the key open. So in other words, you need to connect the wires like this in this particular format. Let us continue with the procedures. So once you've set up the circuit as shown in the diagram above, you set the resistance on the resistance box to R. The value of R will be changing. So the first value of R could be 2, then the second value could be 4, and so on and so forth. So R is the resistance value of the resistance box, and that is going to be changing. So for each value of R, you will close the key and take the readings of the first ammeter and the readings of the second ammeter, and each of the readings will be marked as I1 and I2 respectively. Then once you've got your I1 and I2, you divide I1 by I2 to get your Z, to evaluate Z as I1 over I2. Then you repeat the experiment for various values of R. We are going to set the various values of R in this settings tab. And in each case for R, you measure I1, I2, and you evaluate Z. Then you tabulate your readings. And once you are done with the readings, you plot a graph with R on the vertical axis. Vertical axis means the y-axis, and Z on the horizontal axis, which is the same as the x-axis. Then you determine the slope S of the graph. So these are the steps to be taken in carrying out the experiment. So what are the precautions? It's very important you take note of these precautions because in most physics experiments, you'll be asked to list the precautions taken. So part of the questions might be, what are the precautions to be taken when carrying out this experiment? So here are 4 precautions to be taken. The first one is to ensure that the wires are tightly connected. The second is to remove the key after taking each reading to avoid draining the batteries. So this means once you are done taking readings, remove the key. In other words, switch off the circuit so that the battery will not drain. If the battery drains, your result will not be that accurate because you end up using different uh, e.m.f for different values of R. So ensure you remove the key after taking readings. Then once you're about to take another reading, you insert the key, that is you switch on the circuit. The third precaution is to ensure that error due to parallax is avoided when taking readings from ammeter. So this means when you are reading the ammeter, try to make sure that your eye is aligned with the ammeter so that you don't get reading by the side. So this is very important, especially when you are dealing with analog ammeter. In most NECO experiments, you'll be provided with analog ammeter. But if you happen to have a digital ammeter, then you don't have to worry about error due to parallax. Then avoid zero error of ammeter. I try to take note of zero error of ammeter and take into account. So this means before switching on the circuit, try to know what the ammeter reading is. If the ammeter reading is not exactly on 0, so let's say before switching on the circuit, the value the pointer is on 0.01, for instance. That 0.01 is called 0 error in the sense that the value is not at 0 when current is not flowing. So what that means is whatever reading you are going to get, you should subtract 0.01 from that reading. That's if the initial reading is 0.0 without current flowing. So that's what they call zero error. Try to take note of it if your ammeter has zero error, and try to take that into account when taking down the final reading, when recording the final reading. Okay, so these are the things you have to take note of. Another thing I need to mention here is when expressing the precautions, you should state it, you should personalize it. So you shouldn't state it the way it is here. When stating it in the exam, or try to use expressions like I ensured that the wires were tightly connected. I ensured that the key was removed after taking each reading to avoid draining the batteries. I ensured that error due to parallax was avoided. So try to state it as if you are reporting it personally. Okay, so the next thing I need to explain is this. What's a resistance box? What's ammeter, and how do you take reading from them? And how does a plug key work? How does it work? So let's start with the resistance box. The resistance box enables you to create or to create different resistance right on the box. So unlike a standard resistor that you can't change the resistance, you can change the resistance of a resistance box. You can decide that okay, I want this resistance box to have maybe 10 resistance or 20 resistance and so on. So you can set variable resistance on a resistance box. I'm going to show you how a resistance box looks like and how to actually set different resistance. So let's go to the apparatus section of the Mavinhub Physics Lab. Under the apparatus section, I'm going to go to electricity. Under electricity, I'm going to go to resistance box. So this is a picture of a resistance box. So a resistance box has two terminals. Any of the terminal could be positive or negative. So there is no special negative terminal or special positive. Any of them could be positive and any of them could be negative. And here you have your knobs. Here you have your knobs, and each knob has a resistance value. So how do you set a resistance? You set a resistance by removing a knob. So I'm going to explore a resistor. This is the top of a resistance box. So let's say I want let's say 10 ohms. I'm going to remove this knob. Once I remove this knob, then I'm going to have 10 ohms. So you set the resistance by removing the knob, not by inserting. It's by removing the knob you get your 10 ohms. So you can explore that in physics, in Mavinhub Physics Lab. You can explore that. So take a look at this figure for instance. The reading on this resistance box is 213. How is it 213? This is 200 plus, we remove the knob of 200, we remove the knob of 10, that's 210. Then you remove the knob of 2, that's 212. Then you remove the knob of 1. So altogether 213 ohms. So you can also take a quiz on this on Mavinhub Physics Lab. You can test your ability to take readings on resistance box and other apparatus. So in this case, what is the resistance reading here? So this is 200 plus 20 plus 10, and that is 210. 230 rather. So the next is, let's go to next. What is the reading of this resistance box? This is 200 plus 100, that's 300. 300 plus 20, that's 320 plus another 20, that's 340 plus 5, that's 345, then plus 4, this 2 plus 4, that will give you 349, so 349. Okay, let's talk about the other apparatus, ammeter. What's an ammeter? An ammeter is used to measure current. So an ammeter is designed for measuring current, and you measure current by connecting the ammeter in series to the resistance. So let's take a look at how ammeter looks like, the typical ammeter in most laboratory. So the typical ammeter looks like this. The analog ammeter looks like this. The digital, this is a multimeter. This is a multimeter. You won't be given this type of uh, ammeter most likely. This is the kind of ammeter you most likely be given. So how do you take reading on ammeter? So you look at the main reading. The main reading has 0, 1, 2, 3 up to 10. Now it means each of then look at the division. The division between 0 and 1, how many divisions do you have? You have 1, 2, 3, 4, 5. So you have 5 divisions. So which means each of these are 0.2. So this is 0, then this is 0.2, this is 0.4, and this is 0.6, this is 0.8, and this is 1. So you can know what the smaller divisions, what the values of the smaller division are by knowing how many divisions you have between two major lines. So if you have up to 10 divisions, that means each of the small lines will be 0.1. Okay, let's take a look at, let's do some quiz. You can explore the ammeter here by just sliding it forth and back, and you'll see the reading here, and you'll be able to see what is pointing at. So you can actually gain mastery on how to read ammeter by exploring it on Mavinhub Physics Lab. So let's take a look at, let's answer some questions. So what's the reading of this ammeter? The reading is 4 because it's pointing at 4. Then what is the reading of this? This is 8. So what's the reading of this? This is 5. And it goes on. Okay, so we are going to talk about the next thing is talk about the one-way plug key. So the one-way plug key is something like this. It's something like this. So there's a terminal here. There's another terminal here. That it could be positive or negative. It doesn't really matter. Not any of them could be positive. Any of them could be negative. Then you have your knob. If you insert this knob, that means the current is flowing. That means that's an on state. If you remove it, that's an off. That is an off state. So by inserting the knob, the current flows through the circuit. By removing it, current stops flowing. So it's very important you understand that. And you can explore that in physics lab by just switching it on or off, on or off. Okay, so let's go back to the experiment. So we're going to change the settings of this experiment to match the information provided by NECO. So let's talk about the e.m.f. The e.m.f. given stated here is 1.5 volts times 2 dry cells, so altogether 3 volts. Note that you'll be given 2 dry cells, that's 2 batteries most likely, rather than accumulator. So which means you should prepare your mind on 1.5 volts times 2, that's 3 volts. Okay, so let's set that here. So we're going to make our e.m.f. to be 3 volts. Then we're also told that to be provided with 2 ohms resistor, although it will be concealed, but the value that will be given to you is 2 ohms. Then we were also told that okay, we don't know what the range of readings for the resistance box would be. But in this experiment, we are going to assume that, so we are going to assume that the minimum is 2, the maximum is 10, and the step is 2. Then we are going to assume an internal resistance of 1. Every battery has what is known as internal resistance because when you connect a battery to a circuit, to a closed circuit, the volt, the voltage across the battery drops once the circuit is closed. And the reason why you get a lower voltage when the circuit is closed, that is when current is flowing, is because once current is flowing, this internal resistance of the battery um, limits the flow of current, and as a result drops the voltage. So instead of you having a reading of 3 volts, the e.m.f. might have dropped, might have the internal resistance might have reduced the voltage of the voltage. So we call that new voltage terminal potential difference. That is the voltage when current is flowing through a circuit across a battery or across a cell is known as terminal potential difference. You can get more information about this terminal potential difference and e.m.f. under theory. If you go to the theory section of Mavinhub Physics Lab, you get a lot of information about what is electricity, what a cell, what a primary cell, what an accumulator, Ohm's law, internal resistance, and so on. You get all that information. So let's start the experiment. So note, note that we are using external resistance of 2, we are using e.m.f. of 3, and our resistance box will be varied by a step of 2. And the time we're going to set for this experiment is 30 minutes. So let's get started. So I'm going to start the simulation. So here is the simulation environment. So this is where you vary the resistance of the resistance box. This is where you vary them or vary the resistance. So the reading on this slider is the reading of the resistance box. Then this is where you switch on and off the circuit. So if you, at the moment, the circuit is off, meaning the key is removed. If you click on this, it's going to switch to an on state. So let's take a look at what we're expected to do in this experiment. So once again, we're expected to take the reading of the first ammeter and the second ammeter when the resistance of the resistance box is 2. Then I want to change resistance box to have a resistance of 4, of 6, of 8, and of 10. And for each value of R, we're going to read I1, I2, and compute Z. Note that Z is I1 divided by I2. Okay, so let's go back to the lab. So the first reading on the resistance box that we should set is 2. So we need to take reading when the resistance box is 2. Note that when taking readings, when setting your resistance box, ensure that the switch is off. That is, you remove the key so that you don't drain your battery. Once you're about to take reading, you switch on the the switch, or you insert the plug into the key, and that will allow current to flow. So our ammeter is now producing a reading. Okay, so we're going to take the reading of the first ammeter. So you can use your magnifier to get a clearer picture. So this is 2.7. Okay, it's a little more than 7. So let's say 2.7. Let's say 2.73. So 2.73. So the next reading, which is the reading from the second ammeter, is roughly 1 point. If you count the small lines, you see we have 1, 2, 3. Then it's very close to the fourth line. So it's 1.36, roughly 1.36. Let's say 36/37. So let's say 37, 1.37. Okay, so let's move on to the second. Let's change the value of R. So to do that, don't forget you should switch off the circuit, that is, remove the plug, adjust the value of the resistance box to 4, because that's the next value, to 4. Then you can switch on or insert the plug and take your new reading. So for this new value of R, the reading on the first ammeter is almost is 2 points, roughly 2.1. This is roughly 2.1, 2.1. Then the reading on the second ammeter is less than 1, but it is it's close to 1, but obviously less than 1. That is roughly 0.7. So it's roughly 0.7. So let's take the third reading. You switch off or remove the plug. You increase the resistance, that is, you remove the since we want to get 6, you remove the first plug, which is the plug that is pointing to 1 ohm, and you move the plug pointing to 5 ohm, making 6 altogether. So you switch on or insert the plug of the key, and we'll take the measurements. So the measurement here is less than 2, but it's very, very close to 2. So this is 1 point, very close to 1.9. So let's say 1.9, although it's almost 1.9. So we could say 1.88, something like that. So this is 1.88. Then for the second ammeter, you have a value that's close to 0.5, but let's look at it closely. That is 0. Very close to 0.5, but let's say 0.47. So let's say 0.47. 0.47. So let's change the R to 8. But before you do that, don't forget to switch off or remove the plug. Then change this to 0.28. Change it to 8 to switch on or inside the plug. Then you measure again. So this is very close to 1.8. So but you need to try as much as possible to be very accurate. So this is around 1 point, let's say 77, so very close to 1.8. So let's say 1.77. Then we have the other reading, which is this one. So this is 0. This is very close to this is very close to 0.4, but not up to 0.4. So that's 0. Let's say 35. So it's roughly between 0.3 and 0.4. So let's say 0.35. 0.35. So lastly, we change the value of R. Before we do that, we switch off. We change the value of R to 10. Then we switch this on. So once this is on, you take your reading. So your reading is around 1.7. So this is 1.7. While this is very close to 0.3, is very close to 0.3, so we can say this is roughly 0.28. So this is 1.7 and this is 0.28. Now we've gotten our readings from the ammeter, so it's now time to compute the value of Z. So Z is the ratio between I1 and I2. So let's get our calculator. So for the first Z, we have 2.73 divided by 1.37. So this will give 1.99. So let's say 1.993. Then the second one is 2.1 divided by 0.7. That gives 3. So the next is 1.88 divided by 0.47. So that's 4. The next is 1.77 divided by 0.35 divided by 0.35. That gives 5.057. So 5.057. So lastly, we have 1.7 divided by 0.28. So that gives 6.0. 6.07. Okay, so we've got our readings completed. We've completed the readings. Now let's move on to the graph section. So note that you can access the procedure here, and under the procedure, after taking readings, we are to plot a graph with R on the vertical axis and Z on the horizontal axis. So we are plotting R versus Z, and then we have to compute the slope. So when creating a graph, the first thing you want to do is to set the title. So in this title, we have our graph is the graph of R versus Z. The x-axis label is Z, and it has no units because we divided ammeter, whose ammeter divided by ammeter is like you dividing the same unit, so it has no unit, it's unitless. Then the y-axis has a unit, which is ohm. The unit is ohm. That's the resistance of the resistance box. So once you've sorted out the labels, the next is to define the scale of the graph. So how many units do you want to have on the y-axis and on the x-axis? So one way to get your scale very quickly is to take a look at the minimum and the maximum value on each axis. So this Z is on the x-axis, the R is on the y-axis. So to get the scale of this x-axis, try to count the number of major divisions here. Like the number of this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 divisions here. Then divide. Okay, so that's the first thing you need to note. Then the next thing you want to do is to take the difference between the maximum value on the x-axis, on the table of the x-axis, which is 6.07 minus 1.993. So once you've got that difference, divide it by the number of divisions minus 3. So that 3 is to give room for some kind of padding. So you want to divide that 4.077 by 7. That is, whatever you get, then you round it up. So let me explain what I mean by round up. In every graph, your major division should have values of something like 1 or 2 or 3. In other words, you shouldn't use numbers like 3, numbers like 7 as your units for division. So you should use numbers like 1 or numbers like 2 or numbers like 5 and multiples of that. Multiples of that meaning that you can use 10 as well, or you can use 50, or you can use 0.5 and so on. So in this case, the next highest number after 0.5 is 1. That's the next highest number you can use. So we're going to make our scale on this x-axis to be 1. So 1 means we're going to have a step of 1. That's what it means. Then we're going to start from, let's say, -1. Then we are going to stop at the maximum value plus, let's say, 2. That is plus the 2 times that step. So which means we can stop around 8. But you can also stop at 7 to have a more compact uh, result. But that is up to you. 7 or 8 will still be fine. Okay, so let's talk about the scale of the y-axis. You take the difference between the maximum and minimum, which is 10 minus 2, that will give you 8, divided by 7, that is the number of major division minus 3, that's 7. So that will give you 1.14. Since it's higher than 1, you will use the next value, which is 2. So we'll use a step of 2. So a step of 2 meaning this will be a step of 2. Then we'll start from, let's say, -2 or -3. I'm using -3 because I want to make more room for the y and x intercept to be obtained. Then my highest value will be this 10 plus the step, so which is 12. Okay, so this is what we've got as our scale. So make sure your scale is such that most of your points or your point covers about 50, maybe to 60 or 70% of the graph area. Okay, so let's talk about how to actually locate the point on the graph. So to locate the point on the graph, you start by clicking this pencil sign to indicate that you want to locate the point on the graph. So you start locating. So when the z is 1.99, this is roughly 2. Our r is 2, so which is like saying when z is 2, which is 1.99, which is very close to 2, r is 2, so you can click this point. You can basically click this point. So the next is when z is 3, r is 4. So this is the right point to click. When z is 4, y is the r is 6. So here we have 6. Here we have 6. When z is 5.057, which is roughly 5, z is 8. So you stop, r is 8. When z is 5.057, r is 8, which is roughly this. When z is 6.07, so 6.07, r is 10, so which is roughly this. So we've got our point. So the next thing is to join the point with a line of best fit. So to draw a line of best fit, once you've completed this point, this will indicate green, meaning you are done with it. So let's move on to the line of best fit. To draw a line of best fit, we can start somewhere here or somewhere here and try to join the entire point. So to join the point, you try as much as possible to make sure your line touches all the points. If it doesn't touch the point, make sure the line is as close as possible to all the points, even if it doesn't touch all the points. So here we have okay. The reason why I said to allow this line to cross this the x-intercept and the y-intercept is because part of the question is for me to I'm asked to provide that in the software. The software wants me to indicate the x and y intercept. So that's the reason why I had to stretch it. But if you're not asked to do that, then you just stop somewhere here. Don't stretch it don't let it touch any of the axes if you are not asked for x or y intercept. But if you are asked, then you have to do that. So what's the next thing to do? The next thing to do is to get the slope. So to get the slope, I'm going to click on this slope pencil. Then I'm going to pick 2 points. So I'm going to pick this point and this point. So the 2 points that I'm going to use to compute my slope. So ensure that the 2 points are on the line of best fit. So on this very point, this is the x1 and this is the y1. Then on this point, this is the x1, which is 5. Then the y1 is, sorry, the x2 is 5 and the y2 is 8. When picking points for slope, try to use points that are very close or exactly on the major lines. It makes it very easy to compute your slope. So in this case, our y1 is 4. So this y1, if you try to stretch this to the y-axis, so that's 4. Then your y2 is this other point. Then when you stretch it to touch the y-axis, So that's 8. The difference between y2, that is y2 minus y1, is 4. Then we have this other one, which is 3. The x1 is 3 and the x2 is 5. So this is 3 and x2 is 5. The difference is 2. Okay, so what's the slope? The slope is the difference between the slope is change in y divided by change in x. In other words, if you divide this 4 by 2, you get your slope. So 4 divided by 2 will give you 2. So what about the intercept? The x-intercept is the point where this line of best fit touches the x-axis, so which is 1. And the y-intercept is the point where this line of best fit touches the y-axis, which is minus 2. Okay, so you need to take note of the slope that we've obtained here, which is 2. So we are done with the graph section. Let's move on to the questions. So for the first question, we are asked to use the slope S that we derive from the graph to calculate the resistance R0. If you had read the principles behind this experiment, you would have seen that the slope is actually equal to the resistance. So this experiment is actually leading you towards figuring out the resistance of the standard resistor. So whatever you have as the slope, which is S, is what will be the value of the resistance. So if you check here, you will see that our slope is 2. So R0 is 2. So the next question here is the terminal potential difference, that's PD, of a battery is always greater than the electromotive force of the battery. So in this question, you are asked to say, is that statement true or false? That is, can we say it is true that the terminal potential difference of a battery is always greater than the electromotive force of the battery? The answer here is no. The terminal potential difference is going to be less than, is not going to be greater than the e.m.f of a battery. So this statement is false. It's not greater than. So we're going to say the answer is no. Okay, we're done with the question and also done with the graph and reading. So it's time to submit our work and to see our answer. Note that we spent about 25 minutes on this experiment, so which is not a bad one. The timing will help you to measure how fast you can take readings and how quickly you can finish the experiment. So let's submit. Okay, so this time around I got a very good score. I have 100% readings. I have 98.5% overall score. Then I did well in readings. I made a slight error with my axis. I think I mistakenly moved the axis while dragging this. I moved it slightly and but it doesn't really matter. I still got 83.3%. The software analyzes your every aspect of the graph. It has a very intelligent uh, system that grades you on the spot, that analyzes the experiment and determines what the right axis should be, what the right reading should be, and also tracks your ability to identify the points on the graph. So it's a very, very useful tool for every student that will ever uh, participate in any physics, in any high school physics practical. So let's take a look at the time spent. So I spent 24 minutes 54 seconds. I spent a great deal of my time under the graph section, then followed by the lab section, reading section, and I spent the least time answering questions. So my reading is good to go. So let's take it. The reading in bracket is the computer generated reading. even though I didn't get exactly what the computer got, it still graded me right because I'm still more than 90% close. So that's why there's no red uh, cell here. So this is my graph, and this is the computer generated graph. Very similar. So where we have slight differences, okay, we have very similar value for the axis. I moved the axis slightly, so that's why we have some decimals here. But we still got very similar results. Then let's take a look at the question section. So the answer is 2. That's the resistance of the standard resistor, and the answer for the second question is no. So this is a complete guide on how to perform the 2021 NECO Physics Practical question number 3. This is a complete guide, and um, we've covered every aspect of it, and I strongly recommend you practice and practice until you are confident enough to score at least 90%. So all the best in your exam.